A very good morning to all, and welcome to my class. Today, we are going to discuss chemical kinetics and nuclear chemistry, right? So, basically, in today's class, we are going to see some important concept of chemical kinetics as well as nuclear chemistry and try to solve some numerical based on, right? So, let's see what do you mean by this chemical kinetics and which type of questions they generally ask from this chapter. Okay, so let's start with the today's session. Before this, I hope my voice is audible to you and my screen is also visible to you. If you face any problem, then you will text me. I'll definitely sort out this problem, right? Okay. So basically, what is chemical kinetics, right? So if someone asks, what is chemical kinetics? How will you define? So basically, chemical kinetics is the branch of science which basically deals with the speed, or we say rate of a chemical reaction, right? Or we say the factors which affect the rate of a reaction and the mechanism by which the reaction proceeds. So basically, the chemical kinetics is the branch of science which deals with the speed, or we say rate, or we say the factors which affect the rate of reaction and the mechanism by which the reaction proceeds. So this is all about the chemical kinetics, right? I hope this is clear to you. Hmm? Okay. So basically, how will you define the chemical reaction then? What is chemical reaction basically? So chemical reaction is nothing but chemical reaction involve breaking and formation of the bond, right? So chemical reaction involve breaking and formation of a bond. Therefore, different bond require different amount of energy for breaking and different amount of energy is evolved during the bond formation. Thus, the rate of a different reaction are different. Okay, so if I'm talking about the chemical reaction, so basically chemical reaction means nothing, but it involves the breaking and formation of bond. Therefore, the different bond require different amount of energy to breaking and different amount of energy is evolved during the bond formation. Thus, we can say that the rate of different reactions may be different as well, right? Because every chemical reaction involving breaking and the formation of the bond and the different kinds of bond require different amount of energy for breaking. So we can say that the rate of a different reaction are also different. So we can classify the rate of reaction on the three types, that is instantaneous or fast reaction, average reaction, or we say moderate reaction, and the very slow reaction. So we classify the rate of reaction into the three types. So what is instantaneous or fast reaction basically? So these are in fact a very fast reaction and it is practically impossible to measure the speed of such reaction, right? So these are the in fact very fast reaction and it is practically impossible to measure the speed of such reaction, right? So typical example of such reaction include ionic reaction, organic substitution reaction, and explosive reaction of oxygen with hydrogen and hydrocarbon. So they are typically the example of the instantaneous or we say fast reaction, right? So what do you mean by this term fast reaction, instantaneous reaction? So these are in fact very fast reaction and it is practically impossible to measure the speed of such reaction. And typical example of such reaction include ionic reaction, organic substitution reaction, explosive reaction of oxygen with hydrogen and hydrocarbon, right? Now, what is extremely slow reaction? So what do you mean by this term extremely slow reaction? So such reaction which proceed at a very slow speed, and here the speed is so slow that it is not possible to measure the speed of such reaction. So in case of fast reaction, where also it is impossible to measure the speed of the reaction because the reaction is very fast. But in case of extremely slow reaction is also such reaction proceed at a very slow speed, and here the speed is so slow that again it is not possible to measure the speed of such reaction. For example, rusting of iron. Now, the third one is moderately slow reaction. So this reaction belonging to the third category with the moderate speed, that is inversion of cane sugar and hydrolysis of starch, right? Inversion of cane sugar and hydrolysis of starch. Okay, so these are basically the example of the moderately slow reaction. Okay, I hope this is clear to you. Good. Now, depending upon the number of steps, chemical reaction are classified in the following way. So, in which way you classify the chemical equation basically better? The first one is known as elementary reaction. So what is this elementary reaction? So a balanced chemical equation never give us a true picture of how reaction takes place, right? So whenever some equation is balanced, it will not give us a true picture of how reaction takes place. It can be completely in one step or it take in more than one step, right? So we can't get any idea by just looking the balance equation, right? The reaction taking place in one step are called the elementary step, and the reaction takes place in more than one step are called complex reaction. So these are the reaction in which the atoms, ion or molecule are represented in the balanced chemical equation may or may not together collide simultaneously, right? So basically in complex reaction, these are the reaction in which the atom, ions or molecule as represented in a balanced chemical reaction may not come together to collide simultaneously, right? So maybe they are not colliding with each other at the same time. Okay. So for example, here we'll see that from the example that is 5Br negative plus BrO3 plus 6H plus in aqueous. This will gives us 3Br2 plus 3H2. So it is impossible for all the 12 ions, that is the 5 ions of bromine and 1 ion of BrO3 and 6 ion of H plus 3 and this. So 6 and 6, 5, 11, right? And 1 BrO negative ion, that is total 12 ion. So it is impossible for all the 12 ion of the reactant to come together simultaneously to collide. Such reaction takes place in the sequence of number of steps, and each of this step is an elementary reaction. So remember this point, different step of a complex reaction are a elementary reaction, right? So this is we got the basic idea about what is the difference between the elementary reaction and the complex reaction. So complex reaction is made up of a several steps, and each individual step itself represent the elementary reaction, right? So rate of a chemical reaction. So how will you determine the rate of a chemical reaction? So basically the rate or speed or velocity of a reaction is the rate change of concentration of the reactant or product in a unit time. So this is known as the rate of a reaction, right? So rate of a chemical reaction is nothing but rate or a speed or a velocity, right? The rate or a speed or a velocity of the reaction is the rate of change of concentration of the reactant or product in a unit time. So this is known as the rate of a chemical reaction. When a reaction occurs, the concentration of the reactant start decreasing while the concentration of the product start increasing. Done. So whenever a reaction occurs, the concentration of the reactant start decreasing, okay, while the concentration of the product start increasing. So this point is very important. Always remember, at the beginning, the reactant is 100% and product is 0. As soon as the reaction started, the concentration of the reactant being decreasing, and the concentration of the product start being increasing. So we can define rate of a chemical reaction as, that is the rate of reaction is nothing but decrease in the concentration of the reactant divided by time interval. Or we say rate of reaction we can also define as the increase in the concentration of the product divided by the time interval. So in general, for a reaction N1A will give N2B and produce M1C and M2D, the rate expression may be expressed as 1 upon N1, that is delta A by delta T, or is equal to minus 1 upon N2 delta B by delta. In terms of product, we can write as 1 plus M1 delta C by delta T, 1 plus M2 delta D by delta T. So always remember this, the negative sign indicates that the concentration of the reactant decrease with time, whereas the positive sign indicates that the concentration of the product increase with the time. So they are the significance of this negative and the positive terms. I hope this is clear to you, right? Good. So type of rate of reaction. So let's study the type of rate of reaction. So first one is average rate of reaction. Okay. So what is this average rate of reaction? So basically average rate of reaction is defined as the rate of change of concentration per unit time. And it is calculated by dividing total change in the concentration of any one of the reactant or product by the total time taken to do so. For the reaction, right? For the reaction like this, PCl5, this will give us Cl2 plus PCl3. So what is the average rate of reaction? Average rate of reaction is nothing, but it is equal to decrease in the concentration of PCl5 upon the time taken. It can be also expressed in the terms of PCl3 and Cl2, like rate is equal to nothing but negative of PCl5 because this is reactant. So concentration of reactant decreases as the reaction proceeds, and the concentration of Cl2 and PCl5, as we see, positive sign is here. So concentration of Cl2 upon time, PCl3 upon time, this will be increases. So this is how we can represent the rate of the reaction. Now, the next one is instantaneous rate of reaction, right? So what do you mean by this term, instantaneous rate of reaction? So we know the average rate of reaction. So what is instantaneous? So basically the rate of reaction at any particular instant of time. The rate of reaction at any particular instant of time is known as instantaneous rate of equation. It is equal to small change in concentration, that is dx, in a small interval of time, that is dt. Okay. Now, let's see how will you represent the instantaneous rate of reaction. So we can represent instantaneous rate of reaction like rate is nothing but is equal to dx by dt. In general, for a reaction N1A plus N2B give a M2, M1C plus M2D, instantaneous rate of reaction is represented as 1 upon N1 dx by dt, or we say dA by dt, dB by dt, and plus dC by dt and dt by dt, right? So in aqueous solution, the rate of reaction is not expressed in the terms of change of concentration. So important note here, beta, point to be noted here. This one is very important note. In aqueous solution, the rate of reaction is not expressed in the terms of concentration. Then how will you represent? Because there is a negligible change from 55.5 molar to 55.49 molar, right? So basically in the aqueous solution, the rate of reaction is not expressed in the terms of change of concentration of water because there is a negligible change like 55.5 to 55.49 only. Now, this is going to be very important. That is the unit of rate of reaction. So how will you determine the unit of rate of reaction basically? So rate of reaction has the unit of concentration or molarity divided by time. So this is the basic. So this is the rate of a reaction has the unit of the particular thing, that is concentration or molarity divided by the time. So what is the unit of rate of reaction basically? The unit of rate of reaction is nothing but unit of concentration divided by per unit time, right? So unit of concentration divided by per unit time is known as unit of reaction. So we can represent as that is mole per liter second or mole per liter. How will it come better? We know that. We know that in case of right. Let me write first. If you want to calculate the unit, then we know that this is nothing which is equal to unit of concentration, right? So concentration means anything. Let us assume as this is nothing but delta R upon delta T, right? So this is the concentration. So for concentration, we know that what is the unit of concentration? That is nothing but mole per liter, right? So this is the unit of concentration. And what is delta T? It will be either represented in second or minute. So what the unit come? Mole per liter, or we say mole per liter minute inverse, or we say second inverse. So this is the unit. So these two are the units of this, right? So this is how we'll write the unit of rate of reaction. I hope this is clear to you. Similar in case of gaseous reaction, the unit of rate of reaction become atmospheric second or atmospheric minute. So in place of concentration, if you have a gaseous reactant, then we use ATM, right? So atmospheric second or atmospheric minute, and so on. So what are the factors? Because we know the unit of the rate of reaction, then we are going to study the factors which affect the rate of reaction. So which factors basically affect the rate of reaction, right? So first is concentration of the reactant. So this one is very important. So an increase in the concentration of the reactant always increase the reaction rate, right? So whenever you increase the concentration of the reactant, reaction rate will be increases. The next one is nature of the reactant. The nature of bond, right? The nature of the bond, okay? The nature of the bond in a molecule influences the rate of reaction at which it change into the product, right? So nature of the reactant also play a very important role. The nature of the bond in a simple molecule influences the rate of reaction at which it changes into the product. Okay. Next is temperature. So reaction rate is normally favored by the increase of the temperature. So if you increase the temperature, then the rate of reaction also increase. Right. Next, the temperature effect is expressed in the terms of temperature coefficient. Later we are going to study this thing as well. The temperature effect is expressed in the terms of a temperature coefficient, which is the ratio of the velocity constant of a reaction at a two temperature, which is differ by 10 degrees Celsius, right? So basically the temperature effect is expressed in the terms of temperature coefficient, which is the ratio of the velocity constant of a reaction at a two temperature differ by a 10 degrees Celsius. So temperature coefficient, how will it represent? That is temperature at T plus 10 degrees Celsius are divided by the rate constant at the temperature of T degree. So temperature coefficient is defined as the ratio of rate constant when the temperature is plus by 10 degree upon may rate constant at a temperature T on. Okay. So for most of the reaction, the rate is double for the every 10 degree rise in the temperature. So for the maximum reactions, the rate of reaction become double for every 10-degree rise in temperature. Okay, right. Now, this one is also play a very important role. That is the presence of a catalyst, right? That is the presence of a catalyst. So presence of a catalyst also represent a very important role, right? Okay. How a catalyst is a substance which alters the reaction rate, but itself remain unchanged in amount and a chemical composition at the end of the reaction. Actually, the reactant in a reaction have to cross an energy barrier to form product. And the higher energy barrier, the slower is the rate of reaction, right? So we can represent as like this. That is, yes, we can represent as, yeah, okay. So I hope you understand presence of catalyst, how presence of catalyst affect the rate of reaction. Basically, a catalyst is a substance which alters the reaction rate, but itself remain unchanged in amount and a chemical composition at the end of the reaction. Actually, what happening the reactant in a reaction have to cross an energy barrier to form a product. The higher the energy barrier, the slower is the rate of reaction. So catalysts provide an alternate path of the lower energy barrier. Thus, they make the reaction react to give the product. A catalyst provide a new reaction path with the lower energy barrier so that more and more reactant molecule can form the product. So I hope this is very clear to you. What is the effect of presence of catalyst on the rate of reaction? Right. So basically, catalyst is a substance which alters the rate of reaction, but itself remain unchanged in amount and chemical composition at the end of the reaction. Actually, the reactant in a reaction have to cross an energy barrier to form the product. The higher the energy barrier, slower is the reaction rate. So catalysts what do? They provide a new reaction path. They provide some alternate path. For example, let me show this. If this is the path, right? If this is the path of the reactant to get react to form product, catalyst provide us some alternating path. So this graph with catalyst, this is without catalyst, right? So without catalyst. So this represent without catalyst, this represent with the catalyst. So catalyst provide a alternate path of the lower energy barrier, right? So our catalyst provide a new reaction path with the lower energy barrier so that more and more reactant molecule can be converted into product. Now, the next is the surface area of the reactant. So surface area of the reactant also play a very important role, like the rate of reaction increase as the surface area of the reactant increases, right? So just understand this thing. If the surface area of the reaction being increases, then the rate of reaction also increases. The next one is the presence of light. So reaction rates normally become faster in the presence of light, right? So reaction rate become normally faster in presence of light. So what light gives beta? So light gives us basically light gives the necessary activation energy, right? Light gives us necessary activation energy, okay, for the light to be react. So this one is very important point also, that is the presence of light. So presence of light, how the presence of light actually affect the rate of reaction? So reaction rate normally become faster in the presence of light. So if the reaction carried out in the presence of light, the rate of reaction becomes faster. And light gives the necessary activation energy for starting the reaction, right? So light gives the necessary activation energy for starting the reaction. Now, what is rate law and rate constant? So can you define what is rate law and rate constant? So the mathematical relationship between the rate of reaction and the concentration of the reactant is termed that rate equation or rate law. So this will going to be very, very important topic, right? What is rate law? So basically the mathematical relationship between the rate of reaction and the concentration of the reactant is termed as rate equation or the rate law expression. The rate law for the given action has to be stabilized by experimental study of the rate over the wide range of the concentration of the reactant. So basically the rate law for a given reaction has to be stabilized by experimental study of rate over a wide range of concentration of the reactant. So what is rate law? How will you represent rate law? So basically, let us consider a two reaction that is A plus B. This will give us product B. Now, if A raised to the power alpha and B raised to the power beta are the molar concentration of A and B respectively, then rate is directly proportional to a concentration of A raised to the power alpha, concentration of B raised to the power beta. Or we say this is known as the proportionally constant, or we known as rate constant, where K is a velocity constant or rate constant. Now, if all the concentration are taken as unities, then rate of reaction become rate constant, right? Thus, rate constant is defined as the rate of a reaction when the concentration of each reactant is taken as unity, and it is also known as a specific reaction rate. So, what is the different characteristics of the rate constant are given? So, first, it is a measurable, it is measure of the rate of reaction. Greater is the value of a rate constant, faster is the reaction. Each reaction has a particular value of rate constant at a particular temperature. The value of rate constant for the particular reaction changes with the temperature. And the last, the value of the rate constant for the reaction does not depend upon the concentration of the reactant. Okay, so these one are the very, very important points. So how will you determine the unit of rate constant? Since the dimension of the rate are concentration per unit time and the SI unit of concentration are mole per meter cube or mole per decimeter cube or mole per liter and second for time, we can represent as follow. Right. For the nth order, let's say n is equal to product. So what is rate? Rate comes out to be nothing but k raised to the power n. So what is k? K is nothing but rate upon an. Thus, the dimension of K is equal to the concentration upon rate is nothing but concentration upon time. Our concentration raised to the power n. So this will write as concentration raised to the power 1 minus n time inverse, or we write concentration as mole per liter. So mole per liter n minus 1, and this is S minus 1, nothing. So this is the n of the order of the reaction. So this is how we can write actually, right? So we can write the unit like mole per liter 1 minus n, and this is second inverse. So this is the formula that we are going to use for finding the unit of rate constant. In case of a gaseous reaction, the concentration are expressed in the terms of pressure. We already discussed in the unit of atmosphere. Thus, the rate has the unit of atm per second. So we can say that thus the rate has a unit of atm per second, right? Now, the unit of different rate constant would be listed in the following table so that we get an idea about the different rate constant, right? So for example, let's see if I'm studying for the zero order, first order, second order, and nth order. So for zero order, the unit of rate constant is nothing, but we know that how will you find the unit of K? So unit of K is nothing, but this is equal to mole per liter raised to the power 1 minus n, and this is second inverse, right? So for the zero order, n is equal to 0, this will comes out to be mole, liter inverse, and second inverse. So this is for the zero order, right? Similar for the first order, n is equal to 1, so 1 minus 1 is equal to 0, so this will become 1. So only for the first order, right? For the first order, it is only second inverse. So this is how we can calculate for the any reaction, right? That is mole per liter ki power 1 minus n and the second inverse. Okay, I hope this is clear to you. So this is the unit of K in terms of concentration. If someone wants to calculate the unit of K for a gaseous reaction, then we can calculate as atm per second, or we say second inverse, or we say atm inverse second inverse, atm 1 minus m. So we can remember like this. That is atm and this is second inverse, right? For the zero order. Because this is for nth order, now this formula we use for the nth order. ATM 1 minus n second inverse, right? So for the zero order, it will become ATM. For the first order, it will become only second inverse. For the second order, it will become 1 minus 2, that is ATM minus 1 second inverse. So this is how we can write the form. Clear? Hai? Sure. Now, once you know the rate of reaction, rate law, then you must know about the molecularity and the order of reaction. So what is this? So it can be defined as the number of atoms or a molecule which collide together at the same time for the reaction to occur, right? So it can be defined as the number of atoms or molecule which collide together at the same time for the reaction to occur. Now, reactions are classified in terms of molecularity as unimolecular, bimolecular, tetramolecular, or we say trimolecular as well, depending upon the number of molecule involved in the reaction. If only one molecule involved in the reaction, we say that unimolecular. If the two molecules are involved in this, then it's known as biomolecular. If four, tetra, if three, trimolecular, depending upon the number of molecule involved in the reaction. So I hope this is clear to you. What is molecularity of the reaction? That is the number of atom molecules which collide together at the same time for the reaction to be occur. Now, let's see this is an example of a unimolecular reaction, that is PCl5, right? So PCl5 dissociated to PCl3 plus Cl2. On the similar mode, they are the unimolecular, only this one is present. This is the bimolecular, where CH3COO, C2H5 and NaOH both are present. So these are the biomolecular reaction. Remember this. Okay. Now, what is thermomolecular reaction? That is nothing but 2FeCl3 plus SmCl2. So only a few thermomolecular reaction are known, while not reaction having molecularities more than three is known, because more than three molecule may not mutually collide with each other, right? So basically, molecularity is observed in the lower cases if the number of atom or molecule is greater than three, right? So it is very difficult for them to collide at the same time simultaneously for all the molecules, right? That's why only a few tetramolecular reactions are known, while no reaction having molecularities more than three is known. Okay, so I hope this is clear to you. Now, determination of the molecularity. So, how will you determine the molecularity? So, in case of a simple reaction, that is elementary reaction, the molecularity is simply the sum of the molecules of the different reactant as represented by the balanced chemical equation. So, in case of the simple reaction only, elementary reaction is generally elementary reaction. The molecularity is simply the sum of the molecules of the different reactant as represented by a balanced chemical equation. Now, as we can see that O2 plus F2, it will give O2 plus F2, unimolecular, bimolecular, or this is called termolecular, right? Termolecular. So this is how will you actually calculate this. In case of a complex reaction, that is a multi-step reaction, the slowest step is the rate determining step. Always remember. So the atom molecules or ion participating in the rate determining step determine the molecularity of the reaction. Consider the following, that is HbRO3 plus 6Hi. This will give HbR plus 3H2. So the reaction takes place through the following step. Like the first step when they are treated with Hi, the following step is very slow. And the next two step is very, very fast. Here, the two molecules participating in the solvent, slowest step, thus reaction is of biomolecular type, right? So this is all about this. Next is molecularity of a reaction is always a whole number. Remember this. Molecularity of reaction can never be in fraction. So it can never be in a fraction or zero. It does not provide any idea about the rate or mechanism of the reaction. Molecularity is defined just for the elementary reaction and not for the complex reaction. Always remember. And molecularity is determined only for the molecularity is determined only for the elementary reaction, not for the complex reaction. So I hope this is clear to you. यहाँ तक सबको क्लियर है क्या सबको समझ आया anyone having any kind of doubt you can ask बेटा anyone okay so this is the characteristics of the molecularity right so I hope this is very much clear to you okay good now let's move to the next thing that is order of reaction. So what is this order of reaction basically? What do you mean by this term order of reaction? How will you derive the order of reaction? So basically order of reaction is defined as the sum of the concentration terms on which the rate of a chemical reaction actually depends as observed experimentally, right? Or we say that the order of reaction is given as the sum of the exponent or we say power to which the concentration terms in the rate law equation are raised to express the observed rate reaction that is in the reaction rate expression. How will you see that? Let's see. For example, if the such reaction like the reaction if the reaction is like A plus B, right? A plus B, right? And this will gives us C plus D, right? And now experimentally you find that according to the rate law, rate is nothing but is equal to K concentration of A and raised to the power alpha. And this is B raised to the power beta. Always remember this, there's alpha beta. If maybe it will be 2, it will be 3. So it's not necessary that alpha beta is equal to 2 and 3 only. So these are experimental value, alpha and beta, right? So what is alpha and beta? So order of reaction is nothing but order of reaction is the power of alpha plus beta, right? So this is the order of reaction that is alpha plus beta. So this is how we can actually write the order of reaction. I hope this is clear to you, right? Good. So this is all about beta, right? This is how we can actually solve this. Let me delete. Okay. So this is the order of reaction. So what is the difference between the order of reaction and the molecularity? So the difference is the molecularity, it is the total number of reacting species that is the molecules, atom or ion which bring the chemical change. And what is the order of reaction? So it is the sum of the power of the molar concentration of the reacting species in the rate equation of the reaction. It is theoretical concept. So molecularity is nothing but it is a theoretical concept where the order of reaction it is experimentally determined. So order of reaction cannot be determined theoretically. It is experimental based data, so it can be experimentally determined only. Right? It is always a whole number. So molecularity states that it is always a whole number. An order of reaction it may be whole number or it may be zero. It may be fraction, positive, or maybe negative as well. So order of reaction may be a whole number, maybe fraction, maybe zero, maybe positive, or maybe negative. It is always a whole number molecularity. Okay, next thing. It is meaningful only for the simple reaction or individual step of a complex reaction. So molecularity is basically, it is meaningful only for the simple reaction. Always remember, or individual steps of a complex reaction, right? So it is meaningful only for a simple reaction or individual steps of a complex reaction. The next is, it is meant for the reaction and not for the individual step. Always remember this thing. So this is a big difference between molecularity and order. That is molecularity. It is the meaningful only for the simple reaction, right? Or individual step of a complex reaction. But it is meant for the reaction and not for the individuals. Now, how will this is the differential and integral form of the different order reaction that we are going to see. That is the differential and the integral form of a different order of reaction. So for the general order of reaction, we know that AA and BB, this will give us CCA dt. So here rate is nothing but dr upon dt, which is equal to Ka raised to the power alpha and beta. So this form of the equation is called differential rate equation. Always remember this form of the rate, where rate is equal to dr by dt negative. This form of rate is called differential rate equation. Always remember, right? So it is measured by the determination of the slope of the tangent at a point t in the concentration versus time curve. This makes it difficult to determine the rate law and hence the determination of the order of the reaction, right? So this makes it very difficult to determine the rate law and hence the determination of the order of the reaction. In order to avoid this difficulty, we can integrate the rate equation and obtain integrated rate equation that gives a relation between directly measured experimental quantities and the concentration at different times. Always remember this thing. In order to avoid this difficulty of the differential rate equation, we can integrate the rate equation and obtain the integrated rate equation that give us a relation between directly measured experimental quantities, that is a concentration at the different times. So let's see. The integrated rate equation are the different for the reaction of the different orders. So let's see for the zero order. So reaction in which the concentration of the reactant do not change with the time and hence rate remains constant throughout are said to be zero order reaction. So let's see how will you derive for this, right? So we know that for the zero order, we know that that is rate is nothing, right? That is rate for the zero order. Rate is equal to K and the concentration raised to the power 0. So here rate is equal to K only, right? Rate is equal to K only. What is rate? We know that rate is nothing, but this is equal to dr upon dt. So this is how will you represent the rate, and this is nothing but K. So this is dr, this is minus K dt. So integrate both sides. So integrate both sides. What we get? We get like this is integration of dr. This is integration of minus K and this is dt. So dr we have, dr is nothing but R and this is minus KT plus integrating constant C. So this is R minus dt. We have integration of dt as a t and this is a constant C. So we have to find the value of C. How will you find? By using a boundary condition. So at t is equal to 0, when the time is equal to 0, we know that when the time is equal to 0, what is C? So when the time is equal to 0, basically R is equal to nothing but R naught, which is equal to C. So value of C comes out to be R naught. Just put this. So we have R minus KT plus R naught. Or we say KT is equal to R naught minus R. Or we can say T is equal to R naught का concentration minus R का concentration upon K. So this is the integrated equation for the zero order. So this is how we can actually write the integrated rate equation for the zero order, right? So this is the form we will have to Understand? That is where R naught is the initial concentration, right? This R naught is the initial concentration. And this is the concentration at time t, right? So this is the concentration at the time t. Okay. So this is how we actually represent. So whenever the concentration, let's see what is half-life time, right? So I'm going to derive for the half-life time. So simply we'll derive like we know that what the value will get, which value will get better. So we'll get the value like that is T is equal to R naught minus R upon K. So half-life time. So what is half-life time? So half-life time is nothing, but it is the time in which the reactor reduces half of its initial value, right? Which is the time, yani, in this, the T is become T half and the concentration R is equal to R naught by 2, right? So this is the condition for the half-life time. Always remember this thing because half-life time is the time in which the reactant reduce half of its initial value, right? So it is the time in which they reduce half of its initial value. Okay, so this is the time t. So t is equal to t half and r is equal to r naught by 2. Clear? Okay, so this is t is equal to t half and r is equal to r naught by 2. So just put the value here. So what you will get in place of t, you'll put t half and r naught is like r naught and r is equal to nothing but r naught by 2. And this is again k. So we know that 1 minus half is equal to half. So this is nothing but R naught by 2K, right? So this is the expression for the half-life time in case of the zero order. So we can directly observe that the half-life time is directly proportional to the initial concentration, right? So half-life time is directly proportional to the initial concentration and they are inversely proportional to the rate constant K. I hope this is very much clear to you. Yeah, this one is clear to you, no? Good. So we can write again, right? We can write again as this is how we do write this. Okay. So let's see. So remember in zero order reaction, it is the amount of reactant that change and not the reaction rate, right? Constant throughout the course of the reaction. So always remember this. T half is directly proportional to the A naught. What does it mean? Does the half-life period of zero order reaction is directly right, is directly proportional to the initial concentration. That is T half is directly proportional to A naught. So what you should remember here, in zero order reaction, it is amount of reactant that changes and not the reaction rate. The rate of reaction remains constant throughout the course of the reaction. Okay. So I hope this is clear to you. Good. What is the characteristics of zero order reaction? Okay, so what are the characteristics of zero order reaction, beta? Can anyone tell me what are the characteristics of zero order reaction? Let me see if you face any live streaming problem. Just give me a minute. Just give me a minute. Oh, all fine. Good. So this is the characteristics of a zero order reaction. So what is the characteristics of zero order reaction basically? So rate is independent of the concentration, right? So rate is independent of the concentration. The plot of rate versus the concentration will be straight line and parallel to the concentration axis. The unit of rate of constant for the zero order reaction is nothing but mole per liter second inverse. So this is the unit. The time required to reduce the initial concentration of the reactant to half of its initial value is called half-life time or we say half-life period. So some examples of the zero order reaction like photochemical synthesis of HCl. When the H2 plus Cl2 react in the presence of HNO, they will form 2HCl. Decomposition of ammonia in presence of a catalyst like 2NH3 when they treated with mobilium or a tungsten, they will convert into N2 plus 3H2. So what is first order reaction? Okay. So what is first order reaction? The first order reaction is defined as the reaction in which the rate is determined by the change of one of the concentration term of the reactant only. Right. So this is how will you determine. So in case of first order, we get the relation like this. So we're not going to, derive this portion because it will take so much time. So just remember this, we'll get this. That is K is equal to nothing but 2.303 upon T log A naught by 8. Right. So just remember this. Some can also remember the formula like K is equal to 2.303 divided by T, and this is nothing but log, and this is the R naught upon R, right? Where K naught, where A naught and R naught both are same. They are the initial concentration of the reactant, and A is the or R is the concentration at the given time. Okay, so this is how will you remember for the first order. So the first order, you need to remember the formula of 2.303 upon T log R naught by R. Okay, so this is the how. Actually, this is 2.303 upon T A naught upon A naught minus X, where A naught and A naught is the initial concentration. AT, we can write A naught minus X, that is the concentration of A at any time T, and X is the amount of A reacted at that time, right? So by this, we can remember this. Now, what is the characteristics of the first order reaction? So let's see some characteristics of the first order reaction, like any reaction of the first order must obey above equation, which can be also written as in the form. Right. So we can also write the above formula like in this form. Right. This equation is of a straight line y is equal to mx plus c. And this if log a or log a minus x value are plotted against the time t, the graph obtained should be a straight line. So this is the slope that we'll get in the first order and in first order, right? So the intercept on the y-axis would be on the log a naught, right? The log a naught will be taken along the y-axis and time is taken along the x-axis, right? And this is the slope minus k upon 2.303. So slope is equal to minus k upon 2.303. This minus k represent the negative slope. So the slope is like this, okay? So this is the plot. Thus, if we plot the a naught by a versus t, the timeline graph will get the product like this. So always remember these two graphs. Whenever log a naught, right? Log a naught, or we say log r, or we say log a versus time t graph is given, we can draw the graph as the first figure, right? As we see in the first figure. Similarly, if the plot between the concentration of the two things, that is log a naught upon a, then we plot the straight line, which is in a positive slope, right? Now, the time taken for the completion of the sum fraction of a chain half-life is independent of initial concentration. How will you write? We know that is t half on putting the value, same logic. On putting the value, you get the t is equal to 0.693 upon k. So here we can say that t half is independent of the initial concentration. Where in case of zero order, t half is dependent upon the initial concentration of the reactant. Where in this case, they are independent of the initial concentration of the reactant. Thus, T half is independent of the initial concentration. Since the rate is dependent of the concentration, the unit of rate constant will be time inverse only for the first order, or we say second inverse, or we say hour inverse only. So what are the examples of the first order reaction where we'll see first order? Like decomposition of H2O2. So decomposition of H2O2 to give H2O plus half O2, they are also example of first order. Dissociation of N2O5 to give NO2 and O2, dissociation. Hydrolysis of methyl acetate, inversion of cane sugar, very famous example. Sucrose, and the inversion will take place in the form of glucose and fructose. So these all are the example of the first order. All natural and artificial radioactive decay of unstable nuclei takes place by first order kinetics only, right? So just remember this. Now, let's see if example of the first order, if N naught is the atom of the radioactive element, this we're going to study in the nuclear chemistry, right? So this is the part of nuclear chemistry itself. This is the part of nuclear chemistry. Okay, so if N naught is the atom of the radioactive element present initially, and N is the atom of the radioactive element present after time t, then we'll write also as a formula like K is equal to 2.303 T log N naught by N, where K is a disintegrating constant or we call decay constant, and half-life time is equal to nothing but 0.693 upon K. Thus, half-life period of a radioactive element is independent of initial amount of the element, right? So now the first order gas phase reaction. So the typical first order gas phase reaction, like considering any typical first order gas phase reaction, like when the reactant and product both are in gaseous form. So let P naught be the initial pressure of A at time T0 and PT is the total pressure at time T. So the total pressure which is equal to PT is equal to nothing but PA plus PB plus PC, that is the pressure unit, where PA, PB and PC are the partial pressure of A, B and C respectively. If X atmosphere be the decrease in the presence pressure of A at a time t, and 1 mole of each of B and C is being formed, then increase in the pressure of B and C will be also be X ATM each, right? So it will be the sum of PA plus PB plus PC. Let's see how will you write. Let us suppose if the reaction is like A, which will give us B and C, and all are present in the gaseous phase. So at T is equal to 0 at the beginning of the reaction, pressure of the A is P naught ATM and B L C having a zero pressure because the product was not formed at the time when the time is equal to 0. And so the reaction start progressing and the time goes on as the reaction is started. Let's see P naught minus X ATM of the pressure A. So X ATM pressure and B L C will be formed. So what is total pressure? Total pressure is nothing but it is equal to what beta? It is equal to P naught and minus X plus x plus x. So we'll cancel out. So we'll give P naught plus x. So this is the total pressure what we'll get. That is P naught plus x. So this is one, right? Similar, and x is equal to Pt minus P naught. We can calculate x from this equation. Now where Pa is equal to 2 P naught minus Pt, just put the value of K. So we'll write K is equal to this. Then we get the formula. So this formula is very, very important. That is K is equal to 2.303 upon T. This is log P naught upon 2 P naught minus Pt. So this is very important, right? So this is very, very, very important in terms of numerical point of view. Yeah, this formula you must remember. This formula we use only when the reactant are in gaseous phase. So whenever the reactant are in gaseous phase, we use this formula. Okay, so whenever the reactant is in gaseous phase, we use the formula like this. Now, reaction involving order in fraction. So there are some reaction rate at which is expressed by the fraction of the concentration. So reaction which involving order in fraction. Let's see the example of such reaction. Like CO plus Cl2, this will give CoCl2, and the order for this reaction is 2 into half, that is 2.5. Similar CoCl2, Cl2 plus CO, as the order is given as 1.5. देखो, order of the reaction is totally experimental find value. So you will not have any method. How will you find this value theoretically? So don't worry for this. If in question they are going to ask determine the order, then they give the sufficient data for this, like concentration of the reactant and rate constant, rate of reaction, all these things they are given. Then only you can able to identify. Otherwise, their value is already always given. Like so here the order is comes out to be 2.5 and order is 1.5. Reaction between H2 and D2, so KH2 BD2 is equal to half, right? So this is how we can actually know this. So the conversion of para hydrogen to ortho hydrogen at a high temperature where the rate is equal to kpH2 1.5. The the non-integer value are generally due to the complex nature of the reaction, which involve more than one elementary step. The overall rate law is obtained by combining rate of an individual step. So this is the summary where we'll understand all these things, right? Like what is rate of reaction, what is all these things, right? Let's see. So how will you understand this all these things like in a summary? So basically a different equation corresponding integrated rate equation T half. So in this and a summary, we are going to see all the important things in a one slide only, right? So let's see if the reaction like goes like this. If A react to give the product, then the order of the reaction is zero. For the order zero, then differential equation like dx by dt and integrated equation like kx by dt, right? And t half is equal to, we know that t half comes out to be is nothing but a upon 2k. And the unit of k is, that is mole per liter and second inverse. This is the nature of the plot we get. When you draw the plot between the time and the concentration, we'll get the plot like this. And when the plot with log a minus x, we get the plot like this, right? So this is how we can get in the case of zero order. So this is all about the zero order. Similar, let me choose the pen. Yeah. Similar in case of the first order. This is the differential rate equation like dx upon dt is equal to nothing but kx minus a, k a minus x, and k is equal to 2.303 a upon a minus x. 0.693 upon k is the half lifetime, and this is the unit of k, that is the second inverse, right? This is the second inverse. So we can draw the graph like this, that is time log a minus x. So slope comes out to be k upon 2.303, and the intercept is nothing but log. Similar for the second order, a plus b, this will give the second order. So this will be like dx by dt a minus x raised to the power 2, right? And this integrated equation by k 1 by t a upon a minus x minus 1 upon a, and 1 upon ka is the half lifetime. So we will also get by using the formula, and this is the curve we get, that is slope is equal to nothing but this k, and intercept is equal to 1 by a. Okay, so this is the entire summary of the integrated rate equation, zero order, first order, and all this thing. I hope this is clear to you. Now, this is a very simple question. You all solve this question as well. For the reaction A plus B, the rate law is given by R is equal to this, right? Like R is equal to K. And this is A raised to the power 1 by 2 and B raised to the power 2. So what is the order? So order we can calculate simply as 1 by 2 plus 2. That is alpha plus beta, or we say this is 5 by 2. Right? This is we can calculate. Now our first order reaction is found to have a rate constant. So K is given. K is nothing but 5.5, 10 raised to the power minus 14. Find the half-life. So we know that half-life, what formula for the first order? 0.693 divided by K. So we know the value of K, just put the value of K here and you get the value. Similar such type of reaction, that a first order reaction takes 69.3 minutes for the 50% completion. What is the time needed for the 80% of the completion? So 50% completion first order, we know that that is T half is given. So T half is equal to nothing 0.693 divided by K. So from here you have to calculate K. It comes out to be 0.693, and this will be divided by 69.3. Time is given. So from here you will calculate the value of what? That is the value of K. How it will come? It will come like 693. This is also 693. Above we have using a 10 each, and the downward we're using 1, 2, and 3. Right? So this will become cancel out each other 1 by 100, or we say 0.01. Right? 0.01 K comes out to be. Now, what is the time needed for the 80% of the reaction? So time. So time for the 80% is nothing, but it is equal to 2.303 divided by K, which is comes out to be 0.1, and this is log R naught. Whenever the question is in percentage, always take R naught as 100. And 80% reaction completed, it means 20% is left, right? So just use. If in the question, if they're given 75%, then R naught is always 100. They never be changed, right? And the R become 100 minus 75, that is 25. So you solve this, it is very easy to solve, like 2.303, 0.01. This is log, and this is nothing but log 5. So this is log 5. We know the value of log 5, just put the value, you'll get the answer. So this is very simple question. right? So we can also, yeah. So what is the effect of temperature on a rate of reaction? So we have to study the effect of temperature on the rate of reaction. So rate constant and therefore the rate of a chemical reaction depends strongly on the temperature, right? So typically the rate of all reaction increase with the increase in temperature we already discussed. So in year 80-19, Arrhenius noted that K, that is the rate constant, is the function of temperature only. For the many reaction fit the equation, the K is equal to AE minus E by A2, where E is called a constant called frequency factor because it gives the frequency of the binding collision of the reacting molecule per second per liter, and it is also called the collision number or pre-exponential factor, right? Pre-exponential factor, where R is the gas constant, T is the absolute temperature, and EA is the energy of the activation. The factor E minus EA by RT, this factor minus EA by RT, E minus EA by RT is referred as Boltzmann factor. Always remember this is referred as Boltzmann factor. Remember this, right? So this EA by RT is referred as the Boltzmann factor and gives the fraction of the molecule having energy equal to or greater than the activation energy, right? So this factor, that is EA upon RT, is referred as the Boltzmann factor and gives the fraction of the molecule having energy equal to or greater than the activation energy. The activation energy can also be defined as the energy the activate passive or non-active molecule after its absorption of the minimum energy in access to normal energy of the molecule, right? So basically, what is activation energy? The activation energy can also be defined as the energy that activate passive or non-active molecule after its absorption or minimum energy in access to normal energy of a molecule, which molecule must possess in order to form product on collision. Now, the concept of activation energy gives us an idea whether a given reaction is slow, fast at a given temperature. A reaction which has a lower activation energy proceed at a faster rate at a given temperature or vice versa. Means with the higher a reaction which has a higher activation energy proceed at a slower rate, right? So the difference in the activation energy are mainly responsible for the observed difference in the rate of reaction. So basically the difference in the activation energy responsible for the observed difference in the rate of reaction, right? Let's see. So how will you calculate the activation energy? So activation energy can be calculated by knowing the rate equation of the two different temperatures and assuming that EA and A remains constant. So taking log of both the sides in Arrhenius equation, we get ln K is equal to ln A minus EA by RT, equation 1. And this is similar equation 2, log. So on dividing this, what we'll get this formula, that is log K2 by K1. Log K2 by K1 is equal to EA upon 2.303 R T2 minus T1 upon T1 into T2. So this relation is used when the rate constant at two different temperature are given, and we can write as well. So graphical representation of Arrhenius equation. So how we represent this Arrhenius equation through graph. So Arrhenius equation is the purely the empirical equation, right? So we can represent through a graph as well. Like we can say that the slope is comes out to be minus E upon 2.303 R, and in the y-axis we are taking ln and this. So just by using this formula only, right? This one, yeah. So by using this formula, we can represent this. Just wait for a second. Okay, right? So this is how we can actually represent such thing. Now, the concept of activation energy is applied to a chemical reaction that can be explained by plotting energy against the progress of reaction as shown in the figure below, right? So this is all about the threshold frequency and all these things. So from this graph, you got to know many important things, right? Like this is the reactant, this is A, and this is they want to convert into the product that is C through a intermediate B. So this is called the threshold energy. This is the minimum energy that must be possessed by the any reacted to get reactive from the product. So what is happening here? This is this one is the activation energy for the forward reaction, right? This is the activation energy for the forward reaction. So activation energy for the reverse reaction is also there. So what is there? Activation energy for the forward reaction. So ETH is the threshold energy, that is the minimum energy required to over and above the energy possessed by the reactant in order to cross this energy barrier. So this is known as the energy barrier. And ER is the energy possessed by the reactant. So ER is the energy possessed by the reactant. So what is happening? All the molecule in the reacting species do not have the same kinetic energy. It is not easy to predict the behavior of any one of the molecule. So Boltzmann and James Clerk Maxwell use statics to predict the behavior of a large number of molecules and give Maxwell-Boltzmann distribution curve, as we can show that. That is the fraction of the molecule, and this is the most probable velocity. So the fraction of the molecule like NF upon NK. So NE is equal to number of molecule with the energy E, and NT is equal to total number of the molecules. So peak of the curve corresponds to the most probable kinetic energy. There is a decrease in the number of molecule with the higher energy or the lower energy than this peak value. When the temperature is raised, the curve is broadened out and the peak of the curve moves to the higher energy value. But the area under the curve is in a constant since total probability must be 1 at all the time. So this is how will you actually represent. So by increasing the temperature of the substance, increase the fraction of the molecule which collide with the energy greater than activation energy, right? So let's see some PYQ questions, right? So these all are PYQ questions are of advance. So let's solve this question so that you get some better idea which type of question they generally ask in the paper, right? So let's see the first question. What the first question asks? Consider the following. Let me just wait for a minute. Right. So considering the following reversible reaction A plus B, this will give AB. The activation energy for the backward reaction exceeds that of the forward reaction by 2R. If the pre-exponential factor of the forward reaction is 4 times that of the reverse reaction, the absolute value of delta G naught in joule per mole of the reaction at 300 Kelvin is. So you have to calculate the absolute value of delta G, and by using the right, by using the this given data. So how will you do this beta? Let me write as, we know that A, which is in gaseous form, react with B, which is also in gaseous form, to give AB, right? So A, which is in gaseous form, react with B, which is in a gaseous form, to form AB. Now activation energy of EA is nothing but is equal to 2RT. Now it is also given AR upon AB is equal to 4. If the pre-expansion factor of the is 4 times, it means AF upon AB is equal to 4. This is given in the question, right? Okay. Now we know that what is the relationship between delta G and equilibrium constant. So delta G is nothing but it is equal to minus RT ln K equilibrium. Okay, got it? So how will you get this? Delta G. So delta G is equal to this. Now Kf, that is forward, for forward reaction constant, is equal to AF E minus EA upon RT. Right? This is for forward. Similar for the backward reaction, it is equal to A B E EA upon RT. Right. So this is equal to EA, that is B upon RT. Okay. So this is the exponential factor, that is, this is AF and this is AB. We know their ratio is 3. So what is K equilibrium? Kf upon Kb, we know that. Just put the value, what you will get on dividing all values, will get nothing but K equilibrium is equal to 4 into E square. This is what we get, 4 into E square. And just to put the value of K and Kb, you'll get a 4 into E square, right? Now you get the values like, now just put the value in this equation. So what do you get? That is delta G naught is nothing but minus R T ln and K is equal to 4 into E square. Right. So we know the formula of delta G. What you will do, that is minus RT, and this is nothing but ln 4 plus 2 ln. Right? ln 4 plus 2 ln. So just put the value. When you put the value, you'll get minus 8500 Joule. Because we know the value of everything. R, we know, T, we know, ln values is already given. So we know the value. So just put the value, we'll get the desired answer. Right? Now, for the reaction A, which gives us the product, the plot A and B with the time, temperature, T1 and T2 are given. Right. Now, in this question, they are saying if T2 is greater than T1, the correct statement is assume H naught and delta S are independent of temperature and ratio of ln K at T1 to ln K at T2 are greater than T2 by T1. Here, H, G, and K enthalpy are their usual meaning, right? So you have to identify the correct option according to this, right? So which of the following is the correct option? Now, for the reaction A to give product, right? For the reaction A to give product, and is already given that T2 is greater than T1, right? T2 is greater than T1. Just put the formula like ln K1, ln K2 is greater than T1 divided by T2, right? So ln K1, ln K2 is greater than T1 by T2. Okay. So we can write as T1 ln K1 T2 ln K2, right? So T1 ln K1, T2 ln K2. Now we can, from this, we can also write that because we know delta G is equal to RT ln K only, right? So this is negative of G naught 1 is greater than negative of delta G2 naught. Or we also write the formula like we know delta G is equal to T plus delta S. In thermodynamics, we study this thing. So we can write as minus H naught plus T1 into delta S naught. Taken. So just put the value. So from this, what we'll get basically. So from this, we'll get like that is T1 delta S naught is greater than T2 delta. So what is the option A and C? Which is option A and C? So option A and C is like uh, this one. That is the first one. Yeah, A and C. So this one is the correct option, right? Out of this. Okay. So question third. So what the question third asks basically. So in this question, they are asking, in a biomolecular reaction, the steric factor P was experimentally determined to be 4.5. The correct option among the following are: the activation energy of the reaction is unaffected by the values of a steric factor. Experimentally determined value of the frequency factor is higher than the predicted by the Arrhenius equation. And since P is equal to 4.5, the reaction will not proceed unless an effective catalyst is used. The value of the frequency factor predict the Arrhenius equation is higher than that determined experiment. Right. So let's see that. Here P is equal to nothing but 4.5. Okay, P is nothing but 4.5 here. We know that whenever the P is greater than 1, right? Whenever the P is greater than 1, then K exponential, right? So K exponential upon में K collision is equal to nothing but P. Okay. Now we know that K exponential is equal to P A minus EA upon RT. Right? Similar, A exponential is equal to PA. Right? So we can say that A exponential is greater than A. Exponential is greater than A. Thus, we can say that this is the experimentally determined value, right? So we can say that K experimental is greater than A. So K experimental is also greater than K. So which option is correct? The activation energy of the reaction is unaffected by the value of the steric factor. So this one is 1, and the experimentally determined value of frequency factor is higher than the Arrhenius equation. So this is also correct, right? Okay, so this is how we'll actually solve this. Now, according to our Arrhenius equation, at a higher activation energy, right? According to the Arrhenius equation, at a highest equation, at a higher activation energy usually implies a fast reaction. Okay, the first point is this. And the next one is rate reaction, right? No. This question is basically according to Arrhenius equation, right? Okay, according to Arrhenius equation. Good. So the second one is the rate constant increase with the increasing temperature. Yeah, absolutely correct. This is due to the greater the number of collision whose energy exceeds the activation energy. The next is higher the magnitude of activation energy, the stronger is the temperature dependence of rate constant. And the pre-exponential factor is measure of the rate of which reaction occur. So both this point, that is A, B, C, and D. These all 3 points are absolutely correct. Okay. Now, a closed vessel with the rigid wall containing 1 mole of uranium. So this question is from the basically from the nuclear chemistry. So I'll explain the concept behind this as well. So the uranium 92-30 is given 1 mole of air to 98 Kelvin. Considering a complete decay of to this, the ratio of the final pressure to the initial pressure of the system at 298 Kelvin. So let's see the complete, complete decay. Okay. So we know that what is given here, that is uranium. So what is uranium? Having atomic number 92, and this is 238. So this is uranium. So when they decay, it will convert it into lead, Pb, plus helium, right? Plus helium, plus 6 electron, minus. Okay. Now see, initial moles, or we say this is the initial mole, right? So initial mole is equal to 1 mole, and this is equal to 8 mole. 8 mole of this will produce. So just balance the equation. This is nothing but 82 and 206, right? And here the 8 mole of, so this is atomic number 2, and this is right, and this is on, right? So we can say that total gaseous mole after decomposition is nothing but 8 plus 1. 8 plus 1, that is 9. So ratio of the pressure Pf upon Pi, which is equal to Nf upon Ni, which is equal to 9, right? Which is equal to 9. So this is how we can solve. On the similar basis, this question is try to solve this question. This question is also very easy, right? So try to just solve this question so that you get a better idea how the question actually going to solve. Right? This question is also on the basis of this. Let's discuss this question once so that you can understand. So a plot of the number of neutron n against the number of proton of a stable nuclei exhibit upward deviation from the linearly with the atomic number is greater than 20. For an unstable nuclei having a neutron-proton-neutron ratio has less than 1, possible modes of decay is R. So which mode is possible in this, right? So let's see, the solution is like, which is possible, right? So let's see what we are going to see. Basically, in this process, there is a decrement in proton, which increases the ratio. So in V, there's a k electron capture, right? So orbital of k electron capture. So in this process, there is a decrement in a P, right? Which increases the ratio, like when the A naught, right? And if I'm talking about this one, that is D1, that is beta plus decay. So beta plus decay means what? That is A. This is A, right? This will decompose to give X plus E minus 1 and G. So only these two, that is A and B, right? B and D, sorry, this decay is possible, right? So I hope you understand this thing. Which type of questions were coming? So some questions were coming from the nuclear chemistry where you need to know the concept of radioactivity and the formula that we already discussed, right? And some numericals were coming from the Arrhenius equation where directly, so Arrhenius equation and this one is very, very important also, activation energy. So this point you must keep strong and revise and do questions as much as you can from this topic only so that you can able to learn this thing, right? So I hope you understand this thing. There is no problem in this. If you have any doubt, you can ask me. No? Okay. So let's end this session and tomorrow we are going to start our new chapter that is transition and coordination compound, right? So that's all for today. Try to solve questions as much as you can and revise this concept as well one step, right? So let's meet in the next class where we're discussing on this too. Take care.